and Einstein merges time and space into a single fabric, SpaceTime. And the mathematician Minkowski said, henceforth, time by itself and space by itself are doomed to fade into mere shadows, and what will survive is a sort of a union of the two. That's the only thing that will preserve its reality.
If these were a little bit more precise than what they actually are, the following would be true. That if I take one higher and keep one lower, and wait a little bit, 1, 2, 3, 4, 5, then I bring them together, they are out of phase. The one which is higher is a little bit ahead, the one which is lower is a little bit late. Now I want to make something clear. This is not a funny consequence of a strange theory dreamed by Einstein. This is something which is measured in physical laboratories with clocks a little bit better than yours and mine. We have atomic clocks. Maybe we can have an image of an atomic clock. This is an atomic clock, which have a sufficient precision to measure this effect at 30, 40 centimeters. 2010, this was measured at 30, 40 centimeters of difference of altitude. So it's a fact. It's nothing to do with Einstein ideas or our ideas about space-time. It's a fact that clocks, any kind of clock, anything which evolving, anything that happens faster, high, and slower, low.
Space and time are actual things, real things. Then you should somehow also accept the premise that at the smallest distances, when you look at space and time, it should be rippling and fluctuating and doing all the things that other physical entities should do. So one of the great intellectual projects of the 20th century was try to reconcile these two pictures. Can you build a theory of space and time as real things, as dynamical entities that fluctuate and ripple using quantum mechanical rules like every other physical thing that we know? So this is an exceedingly challenging problem. Space and time, if you believe the rules of quantum mechanics, should be rippling, they should be violently pulling each other apart, all kinds of stuff should be happening, right? And the results of those happenings should somehow imprint themselves eventually on the large-scale structure of the universe and on the night sky. So we'd like to understand all of that. And so there's the gap. There's the gap between quantum theory and general relativity, which tells us space and time are physical entities.
Now, what Einstein understood is that space-time is a thing, is a gravitational field. So it's very much like the electromagnetic field. In fact, Einstein's project was precisely to redo for gravity what Maxwell had done for electricity. So space now is a field, is a thing, but it's also quantum mechanical, so it's made by grains of space. And these grains of space are the quanta, the individual quanta, which make up space and whose bubbling make up space-time.
Now, Roger Penrose posited back in the 70s that the way that very improbable, strange initial state of the universe could be explained is that the laws of nature had a direction of time built into them. The quantum gravity laws that Vijay and Carla were talking about had a direction of time built into them. But that could only be if time somehow existed at the level of the fundamental laws. If time was emergent from the fundamental laws, then the distinction between the past and the future could not be written into the fundamental laws because there would be no time for them to refer to. So that's another reason that has convinced me, thinking about it, that time has to be deeper than the things which are emergent from the laws. Now we agree, I think all of us, that space could be emergent, but it's much trickier to get time to be emergent with the properties of time in this universe. So let me stop there.
But most of us in physics are very practical operationalists, right? Really, a thing makes sense if you can use it as a calculational scheme for making predictions, for computing things. So one thing that I think that we've not perhaps completely addressed is what that would mean in terms of time being emergent, and how you would use it in some sort of predictive way, and things of that kind. So I think it's first important to state that in something like string theory, which is another approach to quantum gravity, in most approaches to string theory, space and time are taken as operationally real. I mean, just there. There's no need to talk about emergence. It's a stage, and really what those in that field you do is the following. So here's this surface of the stage. If I kick it, a little ripple runs off. And you can build a quantum theory of those ripples. You can do that with space. You bang space a bit, and these little ripples run off, and you call those gravitons, and you build a quantum theory of those ripples. But in the language that I just used, the space and time are pre-existing, right? They're there, right? It's not addressing these deeper questions that Carlo and Lee have been talking about, is where did the space and time come from? You take it to be there, and the project is to build the theory of the ripples on that. Now, in terms of emergence, indeed, as you were saying, there are completely concrete examples in string theory of emergence of space. So it's useful to visualize what that means to then talk about why, emergence of time is such a more complicated thing. So you have lots of examples like this in space, but getting a version of this for time has proved much more challenging because you would need a timeless theory, right? Something without a time in it, in which you need to represent objects in such a way that they effectively carry out these sort of causal interaction. Things can, if they're far away, they can interact after a certain amount of time. So operationalizing that in that kind of sense has proved hard.
That ultimately, these seemingly philosophical differences will be resolvable with evidence.
Well, that's what it takes for it to be science.
And when we finally understand these things, we will have a view of time as essential in a way that it can't be removed, and the notion of the present, of passage, the objective distinction between the past and the present, will be fundamental to physics at an operational experimental level. That's my dream. I think we all share this. We're confident in the power of the tradition of science to come eventually to consensus when we're forced to by experiment. And we hope that that will come even with these difficult questions.